Hello, this is my Physics Lab 2 lab report presentation. So, a little introduction. We used a paper ball and we tracked it throughout its flight in this lab. And I tracked and analyzed the motion through Tracker to get all the data. And then, of course, used GlowScript to compare the actual real life data to the calculated data. And to use the calculated data, I found some formulas we needed. Of course, the net force is, of course, for the first model, is just the force of gravity. And then the second model, we add drag. Because it was a paper ball, the drag is very impactful on it because the mass is so small, less than a gram, or 5 grams, excuse me. And our force time of gravity is mass times gravitational acceleration, of course. And then a force of drag is negative BV squared. Um, and it was found the paper ball did not reach terminal velocity during the fall because, of course, that it is a paper ball, so the drag is so exceptional it can't. Our tracker data here we have the paper ball we threw, and it gave us this data. And here's our graph and some more tracker data. So we can bring into GlowScript now. This is what I wanted to show. Here in Model 1, we have just our sort of more unrealistic, if it was in a vacuum, where there's no drag. And the difference between the codes is that the values are made up of FNet, and the top image, it does not take drag into account. The bottom one does. And you can see that, where is it? Here, where force of drag equals negative B times ball velocity, with our FNet equals W plus FD. So this section takes into account all of drag, which affects our net force due to Newton's second law. And then that's applied to Newton's second law and the momentum principle here with these couple of lines. And then we have our position and model. Our model deviates slightly. Same here. We have our position and the position with the drag. And what the reason that there's more forces in contact is than just the drag and the gravity is because there could have been wind, there could have been a error in the tracker data, and this comes out in potential errors. So our object size and visibility, the small size of the paper ball made it difficult for the camera to get it very clearly, so it could be a little blurry, so the tracker might be off. And it was short duration during the toss and the fall, because it was only a brief period of time, so it limited the visibility of the effects of the air resistance. And a longer toss or longer fall may have had more impact for the drag because the drag force had a longer time period to be able to be exerted over. And then the mass-related discrepancy. If the paper's ball was mass was measured improperly, then the drag is most certainly off, and that just compounds other sources of error. Excuse me, and that can drastically affect results, as we saw here and here. How the calculated data is slightly different than our real data. Now, what does this mean? So within the time frame and the errors, of course, that stated before, the paper ball did not experience terminal velocity. It was given a greater span of time and space. It may get to that point. And the initial throw was introduced, and it shortened the time span, which gave us less time here. You see, we have our initial velocity, and our velocity is constant in the x direction. But in the y direction, you see our position is a parabola, which means that the acceleration due to gravity is pulling it down towards Earth, slowing it down. So from the positive velocity, bring it down to 0, and then to negative velocity. But now I'm curious, what if the paper ball has been thrown up? Then the terminal velocity would not change as it was falling, because when you throw the ball upwards, it is at the same spot as the apex right here in this graph. So that if you toss it from 1 foot underneath, if you toss it from 100 feet underneath, it doesn't matter, because at the top of the apex on your graph, it'll be the exact same because all of the energy is now potential gravitational energy, which can be transferred down into acceleration to the Earth. So the so what if it was thrown up? I think it could reach a constant velocity that is very fast, but terminal velocity may be affected because, I mean, of course, we still have drag. And on a paper ball, like the one we used here, if you can see pretty closely, that paper ball is a lot of area, a lot of surface area for drag to affect it, and very little mass. So we have extreme differences in our data on our models. See how much drag is affected, and that model will result in a change in our terminal velocity. Thank you.